A sudden burst of radio energy screams from the silent void. This signal, and others like it, do not come from stars or planets. They emerge from the darkest, coldest places in our galaxy, interstellar molecular clouds. These vast nebulous nurseries where stars are born are broadcasting mysteries we are only beginning to hear. By the end of this journey, you will know the 25 most baffling signals ever detected from these cosmic clouds, signals that challenge everything we think we know about the universe. Why would the birthplaces of stars send out coherent radio whispers or pulses of gamma rays with no clear source? What strange chemistry is writing messages in light we cannot yet translate? The cosmos is speaking from the shadows, and we are finally learning to listen. What do you believe is waiting for us in the dark? The most famous cosmic shout came on a quiet summer night in 1977. An astronomer named Jerry Eman was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope was silently listening to the sky, and its printout was a long scroll of letters and numbers, a code for the strength of the radio noise it heard. Most of it read like static, but then Eman's eyes landed on a single line, a sequence so powerful and so strange that he simply circled it in red pen and wrote one word beside it. Wow. That word gave the signal its immortal name. The wow signal was a narrow-band radio burst, a pure tone screaming from the void for 72 seconds. It was 30 times stronger than the background noise of space itself. And then, just as suddenly as it arrived, it vanished, never to be heard again. Its origin point was not a star or a known planet. It came from the direction of the constellation Sagittarius, a region of our Milky Way absolutely packed with dark, sprawling interstellar molecular clouds. This is the crucial detail often overlooked. The most famous candidate for an alien message in history did not come from an empty point in space. It emerged from the shadowy, gas-filled nurseries where stars are born. Could the signal have been generated by something natural within one of those clouds? Some scientists point to a rare event, like a comet's hydrogen cloud passing through the telescope's view, but no known comet was in that position. Others suggest a freak emission from a rotating neutron star or an exotic chemical reaction within the cloud's dense heart. Yet none of these explanations fully fit the signal's unique, powerful, and singular profile. The tantalizing, though profoundly unlikely idea is that it was artificial, a beacon, a one-time shout from a technology we cannot comprehend, perhaps nestled within or behind that cosmic fog. The enduring power of the wow signal lies in its perfect mystery. It was a brief, brilliant flare of the impossible, pointing directly at the universe's most fertile and least understood structures. It asks us a haunting question. Was it a natural phenomenon so rare we have never seen its like again? Or was it a message from the darkness, sent once and never repeated? Its silence since that night is as loud as the signal itself. The wow signal was a singular event, a cosmic shout that left only silence in its wake. But what if the universe was not just shouting, but whispering rapid-fire secrets we were not even equipped to hear? For decades, brief blips in radio telescope data were dismissed as earthly interference, satellite glitches, or simple instrument error. They were the static of the cosmos, ignored and scrubbed from the records. That all changed in 2007, when a young astronomer named Duncan Lorimer and his student David Narkovich decided to dig through 6-year-old archival data from the Parkes radio telescope in Australia. They were not looking for anomalies. They were looking for pulsars. What they found instead was a pulse of a different kind entirely. Buried in the noise was a 5-millisecond blast of radio energy so intense, so powerful, that it defied all explanation. In that fleeting instant, it released more energy than our sun puts out in an entire month. They called it the Lorimer burst, and it became the first officially recognized fast radio burst. This was not a sustained tone like the wow signal. This was a cosmic gunshot. Its origin was traced back to a distant galaxy, but the path it took to reach us was not empty. The signal's radio waves were stretched and scattered, a phenomenon called dispersion, which told astronomers it had traveled through a colossal amount of diffuse matter. This matter, many scientists now believe, could be the vast, magnetized filaments of giant molecular clouds, either within its host galaxy or floating in the intergalactic void. Think of it like a lighthouse beam piercing a thick, swirling fog. The fog does not create the light, but it shapes how we see it, smearing its colors and scattering its glow. For fast radio bursts, dense molecular clouds act as that cosmic fog. They can disperse the signal's different radio frequencies, delay its arrival, and even magnify it through natural lensing effects. This realization turned the search for fast radio burst origins into a hunt within the shadows. Astronomers now meticulously scan the directions of these bursts, looking for the telltale murk of star-forming regions. Could the source itself be hidden deep inside such a cloud? Some leading theories point to catastrophic events involving the most magnetic objects in the universe, magnetars, which are the collapsed, spinning cores of dead stars. A starquake on a young, hyper-magnetized neutron star, perhaps still swaddled in the gaseous remnants of the cloud it was born from, could unleash such a titanic flash. Or perhaps it is the violent birth of a black hole, a final scream from a massive star within its dusty stellar nursery. The Lorimer burst did more than discover a new phenomenon. It unveiled a universe crackling with ephemeral violence, and it taught us that to understand these brilliant flashes, we must often look toward the darkest, most crowded places in the cosmos. The clouds are not just silent nurseries, they are cosmic amplifiers and shrouds, hiding the engines of some of the most powerful explosions we have ever detected. The Lorimer burst was a solitary gunshot echoing across cosmic distances, a one-time event we could never study again. But then, a signal began to talk back. In 2016, astronomers confirmed something unprecedented. A source catalogued as FRB 121102 was not just repeating, it was chattering. This was not a single catastrophic explosion. It was a persistent, sporadic voice in the dark, sending out dozens of brilliant millisecond flashes over years. For the first time, we could point a telescope at a specific spot in the sky and wait, knowing another flash might come. And when they pinpointed its home, the location was profoundly telling. FRB 121102 lives in a tiny, faint dwarf galaxy over 3 billion light-years away. But it is not anywhere in that galaxy. It is positioned squarely in a ferociously active star-forming region, a seething cauldron of gas and dust where massive molecular clouds are collapsing to birth new suns. This localization changed everything. It directly tied the engine of these mysterious bursts to the very environments we have been discussing, the dense, chaotic nurseries of stars. The repeating nature of the signal immediately ruled out any explanation that involved a one-time destruction, like a star exploding or two neutron stars colliding. You cannot collide the same two stars twice. So what, nestled inside that violent stellar nursery, could be firing off these incredibly powerful radio salvos again and again? The leading suspect is a magnetar, an intensely magnetic type of neutron star. Imagine the collapsed core of a giant star, spinning rapidly, with a magnetic field 1,000 trillion times stronger than Earth's. Now imagine that star is young, perhaps still surrounded by the debris and intense magnetic fields of the molecular cloud it was born from. Theorists suggest that if such a magnetar were occasionally showered by material from a nearby companion star or from the cloud itself, it could trigger colossal starquakes on its surface, releasing these bursts of radio energy like cosmic lightning strikes. Another possibility is a neutron star, or black hole orbiting through a dense, windy environment within the cloud, its magnetic field interacting violently with the surrounding gas to create repeating shock waves. FRB 121102 taught us that these bursts are not always death cries. They can be the persistent, erratic heartbeat of an extreme object thriving within the most tumultuous neighborhoods of the universe. The clouds are not just hiding these engines, they may be actively feeding them, providing the fuel and the chaotic conditions needed for such spectacular, repeating fireworks. This single chattering source transformed fast radio bursts from cosmic mysteries into tangible, observable phenomena, and it whispered a crucial clue: look for the nurseries, and you will find the source. The repeating fast radio burst was a revelation, but it still seemed random, an erratic cosmic heartbeat. Then, a telescope in Canada began to hear a rhythm. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is a revolutionary instrument, a stationary array of metal cylinders that scans the entire northern sky each day. Its primary mission is to map cosmic hydrogen, but it has become the most prolific hunter of fast radio bursts in history. And among the hundreds of bursts it has captured, one stood out for its impossible regularity. Catalogued as FRB 180916, this source does not just repeat, it follows a strict schedule. For roughly 4 days, it fires off bursts, sometimes several per hour. Then, it falls completely silent for 12 days. After that 16-day cycle concludes, it starts all over again. This is not a suggestion of pattern. It is a precise, predictable clockwork in the chaos of the cosmos. Such a clean periodicity points overwhelmingly to one thing: orbital motion. Something is on a 16-day orbit around something else, and its bursts are only visible from Earth during a specific phase of that orbit. The leading theory places this source within a binary system, a pair of objects locked in a gravitational dance. And where might such a violent binary system reside? Often within the dense, turbulent environment of a massive molecular cloud. One compelling scenario involves a highly magnetized neutron star, the likely burst engine, in orbit with a massive, young OB star. These OB stars are behemoths, dozens of times more massive than our Sun, and they live fast and die young, embedded in the stellar nurseries where they formed. The OB star blows out a ferocious stellar wind, a constant stream of charged particles. As the neutron star swings along its 16-day orbit, it plunges through this dense wind at certain points. When it does, the interaction between its immense magnetic field and the wind could trigger the bursts, like a lighthouse beam flashing only when it passes through a patch of thick fog. Alternatively, the companion could be a black hole, with the neutron star periodically passing through a disk of gas and dust swirling around the black hole's event horizon. That dense material, possibly fed by the surrounding molecular cloud, could act as a shutter, only allowing the radio flashes to escape at a specific orbital phase. The 16-day cycle of FRB 180916 is a profound clue. It tells us that the environment around the burst source is not static. It is dynamic and structured. The molecular cloud is not a passive backdrop. It is an active participant, potentially supplying the material and the precise conditions that create this celestial metronome. We are no longer just listening to random explosions. We are beginning to discern the orbital mechanics of cosmic powerhouses, their rhythms dictated by the very clouds that gave them birth. Rhythms and repeating patterns offer one kind of clue, but the search for artificial signals requires a different kind of listening. It requires listening for a signal that makes no natural sense at all. This brings us to one of the most tantalizing and frustrating entries in the catalogue of cosmic mysteries, a signal known only by a string of letters and numbers, SHGB 02+14a. Detected in 2003 by the SETI at Home project, which uses idle home computers to analyze radio telescope data, this signal sparked immediate intrigue. It was a narrowband radio whisper, centered on a frequency of about 1,420 megahertz. That number is not random. It is the resonant frequency of hydrogen, the most common element in the universe. The logic was elegant, a universal calling card. Any civilization with a basic understanding of physics might think to broadcast on that channel, knowing other astronomers would be listening there. The signals seemed to originate from a point between the constellations Pisces and Aries, a region of space not known for bright stars, but one that is threaded with the faint, diffuse gas of interstellar molecular clouds. For a moment, it looked like the real deal. But science thrives on skepticism, and the closer astronomers looked, the more the signal's flaws emerged. First was its drift rate, the way its frequency changed slightly over time. This drift was consistent with a transmitter on a planet rotating rapidly, which is plausible, but the rate was odd and did not match any known celestial motion precisely. More damning was the signal's profound weakness. It was so faint, it hovered right at the threshold of what the telescope could detect, appearing and disappearing in the data, never strong enough to be confirmed by a second instrument. This made it a prime candidate for the most mundane explanation of all, terrestrial radio interference. A passing satellite, a glitch from a distant airplane, or even a malfunctioning microwave oven in the observatory cafeteria could have mimicked such a faint, drifting whisper. Yet the location still gives pause. Could it have been a natural but unknown process within one of those quiet molecular clouds? A complex chemical reaction or a rare magnetic reconnection event might produce a fleeting narrowband emission. We simply do not know all the ways cold hydrogen gas can speak. SHGB 02+14 remains the ghost in the machine, a perfect symbol of the search for extraterrestrial intelligence. It embodies the heartbreaking cycle of hope and analysis, where a signal with seemingly perfect characteristics dissolves under scrutiny into probable noise. It teaches a critical lesson: the darkest, quietest places in space, the molecular clouds, can produce radio signatures that trick even our most sophisticated algorithms. The search continues, not just for a clear, strong signal, but for one that can survive the brutal gauntlet of verification, a signal that refuses to be explained away by the clouds or our own earthly clutter. The ghostly whisper of SHGB 02+14a represents one extreme of the cosmic signal spectrum, a faint and debatable murmur. But what if the clouds themselves were glowing with a light we could not explain, a pervasive, undeniable shine across the entire sky? This brings us to a mystery not of singular bursts, but of a universal haze. For decades, astronomers mapping the heavens in microwave light, the kind of gentle energy left over from the Big Bang itself, kept finding an extra component of light they could not account for. It was a faint, diffuse glow emanating from numerous interstellar molecular clouds, like the vast Perseus cloud complex. They called it anomalous microwave emission. The anomalous part is crucial. This was not the expected warmth of dust grains, which radiate a predictable thermal signature. Nor was it the clear signal of spinning molecules. This was something entirely new, a mysterious hum coming from the cold, dark nurseries themselves. Think of it like walking into a familiar, dimly lit room and discovering the walls are emitting a soft, steady light you have never noticed before. The source is everywhere and nowhere specific, a fundamental property of the room you had overlooked. For years, the origin of this glow was a major puzzle. Then, a fascinating and almost whimsical theory emerged from the laboratory. What if the clouds were filled with unimaginable amounts of tiny, spinning diamonds? Not the glittering gems in a jewelry store, but nanodiamonds, carbon crystals smaller than a virus, formed in the chaotic atmospheres of dying stars and scattered into space. The theory suggests that these nanodiamonds, tumbling in the magnetic fields of molecular clouds, could spin at incredible rates, emitting microwaves in the process. It is a startling image. Entire nebulous nurseries glittering with a dust of celestial diamonds, their collective spin creating a microwave whisper. Another leading candidate is a class of large, hardy molecules known as polycyclic aromatic hydrocarbons, or PAHs. These are flat, plate-like molecules of carbon and hydrogen, thought to be abundant in space, essentially soot from stellar processes. When these PAHs are zapped by ultraviolet light from nearby stars, they can spin rapidly and emit microwave radiation as they slow down. So the mystery glow could be the collective hum of countless trillions of microscopic carbon frisbees spinning down inside the dark clouds. The research is intensely active because identifying the true source is not just about solving a puzzle. It is about inventorying the very building blocks of galaxies. These molecules and dust grains are the raw materials for new stars and planets. If molecular clouds are filled with nanodiamonds or vast clouds of complex organic molecules, it changes our understanding of the ingredients available when solar systems form. The anomalous microwave emission is a reminder that sometimes the biggest mysteries are not the brilliant flashes, but the soft, persistent background hum of the universe, a signal woven into the fabric of the darkness itself. That soft, universal glow of anomalous microwave emission is a whisper from the darkness, but sometimes a single dark cloud speaks with a stranger, more distinct voice. Drifting in the constellation Ophiuchus, there is a patch of sky so utterly black it looks like a hole punched through the Milky Way. This is Barnard 68, a Bock globule, one of the coldest, most isolated molecular clouds known, with temperatures hovering just a few degrees above absolute zero, and so dense that not a single star shines from within. It is the closest thing to pure nothingness we can observe. It should be silent, a frozen vault of darkness. Yet, when radio telescopes turned their attention to this cosmic void, they heard something unexpected. Faint, structured radio waves seemed to emanate from its heart, not as a steady hum, but with a subtle, complex signature that some astronomers described as having an almost echo-like quality. It was as if the cloud itself was ringing very softly. This presents a profound contradiction. Cold, dark clouds like Barnard 68 are not supposed to be sources of radio emission. They are too cold for thermal processes to generate such signals, and they lack the internal stellar engines that power emission in brighter nebulae. So what could possibly be causing a frozen vault of gas and dust to sing a faint radio song? One compelling line of investigation points to cosmic rays, high-energy particles that constantly rain down from all directions in space. As these powerful particles slam into the ultra-dense heart of Barnard 68, they could collide with the hydrogen molecules within, briefly energizing them and causing them to emit a faint radio whisper. The cloud's immense density acts like a target, making these rare interactions slightly more probable and detectable. Another possibility is that the cloud is not as empty as it appears. Deep within its opaque core, shielded by countless layers of dust, a protostar could be struggling to ignite. This hidden embryo of a star, still collapsing under its own gravity, might generate weak magnetic fields or produce shocks in the surrounding gas that create the observed radio structure. We would not see its light, but we might hear the faint electromagnetic stirrings of its birth. Perhaps the most intriguing idea involves the dust itself. At temperatures so close to absolute zero, and under the immense pressure within the cloud, the behavior of matter enters a strange quantum realm. Certain types of dust grains, coated in layers of frozen molecules like water ice, might exhibit novel properties. The faint, structured radio signal could be the signature of quantum tunneling effects or collective vibrations within this frozen matrix, a purely physical process we have yet to fully understand. The boomerang signal from Barnard 68 challenges our assumptions about silence. It tells us that even the most inert, frozen objects in the cosmos may have a subtle, complex voice. A voice that speaks of hidden impacts, secret births, or physics operating at the very edge of existence. Listening to the darkest places requires hearing not just the loud bangs, but the softest, most unexpected echoes. Barnard 68 whispers of hidden physics in the deepest cold, but other clouds broadcast their mysteries in a language of pure light, a code we are still struggling to crack. In the constellation Taurus, a sprawling dark nebula known as the Taurus Molecular Cloud drifts silently. Within its core, a particularly dense filament called TMC1 is a treasure trove for astrochemists. They study it not with ears, but with eyes tuned to specific colors. This is the realm of molecular spectroscopy. Every type of molecule in the universe, from simple hydrogen to complex carbon chains, has a unique fingerprint. When light from a background star passes through a cloud like TMC1, the molecules within grab specific, precise frequencies of that light. The result is a barcode of dark lines etched across the spectrum, each line a direct signature of a specific chemical. It is how we know these clouds are filled with things like water, ammonia, and even alcohol. But in the barcode of TMC1, there are lines that do not match anything in our earthly laboratory catalogs. They are unexplained spectral lines, ghostly signatures with no known molecule to claim them. It is as if you were analyzing a complex perfume and could identify rose, sandalwood, and vanilla, but were left with a haunting, beautiful scent you have never encountered and cannot name. The hunt to identify these lines is one of the most exciting detective stories in modern astronomy. The prime suspects are large, complex organic molecules, the very types of carbon-based compounds that are the building blocks of life. In the frigid, near-perfect vacuum of a molecular cloud, chemistry works in slow motion. Atoms and simple molecules stick to the surfaces of dust grains, forming icy mantles. Over millions of years, bathed in faint starlight and cosmic rays, these ices can undergo reactions, building larger and more complex structures. TMC1 is unusually rich in long carbon chain molecules, suggesting it is a factory for this kind of cold chemistry. The unidentified lines could be the fingerprints of molecules too fragile or too exotic to exist for long in a warm laboratory on Earth. They might be intermediates in chemical pathways we have not yet conceived, fleeting shapes assembled in the dark. Some researchers even speculate they could point to entirely new branches of chemical physics, quantum mechanical behaviors unique to the extreme conditions of these interstellar laboratories, where temperatures are just a few degrees above absolute zero and densities are 1 trillion times thinner than our air. Every unidentified line is a potential door to a new realm of chemistry. Finding the molecule that creates it is not just about completing a catalog, it is about discovering a new piece of the cosmic recipe, a compound that might one day end up in the primordial soup of a newborn planet. The dark lines in the light from Taurus are more than just missing data. They are signposts pointing toward the unknown ingredients of creation itself, waiting in the frozen dark to be named. The mysterious barcode of TMC1 reveals chemistry in the dark. But what happens when the cloud's work is done and a new star begins to shine? Within the stellar nurseries themselves, the story does not end with the birth of a star. It enters a new, even more intricate chapter as the leftover gas and dust swirl into a flattened disk, a celestial workshop where planets are forged. These protoplanetary disks, embedded within molecular clouds like the Great Orion Nebula, are where the raw materials of nebulae are transformed into worlds. And here, astronomers are finding signals just as puzzling as any from the dark clouds. In the infrared and radio light from these disks, scientists keep detecting strange, unexplained emission features. For lack of a better name, they simply call them X features. These are not the clean spectral lines of a known molecule. They are broad, often bumpy additions to the expected light signature, like unexpected colors smeared across the canvas of a disk's spectrum. They are something new, something happening in the dynamic environment where starlight meets primordial dust. One compelling theory points to the very process we are hoping to witness, planet formation itself. As a young, massive planet coalesces within the disk, its gravity carves a path, clearing a gap in the dust and gas. The material at the edges of this gap can pile up, creating pressure, bumps, and vortices. These dense regions, heated by the young star and agitated by the planet's gravity, could emit a complex mix of radiation, producing the mysterious X feature. It would be the infrared and radio cry of a world taking shape, a signal of creation in progress. But planets are not the only possible sculptors. The X features might be the signature of the dust grains themselves, undergoing a radical transformation. In the warmer, more energetic environment close to the star, simple dust particles can begin to stick together, forming larger, fluffy aggregates or intricate, porous structures. These new architectures would interact with light in novel ways, their infrared and radio emissions creating a signature we have not yet catalogued. It could be the glow of the first pebbles on the path to becoming planets. Perhaps the most chemically intriguing idea brings us back to those icy mantles from the dark clouds. As the protoplanetary disk forms, these ice-covered dust grains are delivered into its mix. When warmed by the new star, the ices begin to evaporate, but not simply. They may undergo a cascade of rapid, complex chemistry right on the grain surfaces, forming new, temporary molecules or creating exotic crystalline structures that emit a distinctive signal before they are destroyed or incorporated into larger bodies. The X feature, then, could be the flash of interstellar ice melting into the recipe for a planet. Each of these theories, from hidden planets to transforming dust, tells us that a protoplanetary disk is not a quiet, smooth pool of material. It is a chaotic construction site, buzzing with physical and chemical activity we are only starting to perceive. The X features are like overheard conversations from that site, spoken in a dialect we have not yet fully learned. They remind us that the transition from a dark, cold cloud to a bright, warm solar system is written in a language of light we are still deciphering, one mysterious spectral bump at a time. Deep within the swirling chaos of a stellar nursery, a natural laser fires a perfectly coherent beam across the cosmos. This is not science fiction, but a common, though utterly strange, phenomenon called an astrophysical maser. The word maser stands for microwave amplification by stimulated emission of radiation. It is the microwave cousin of a laser, and space is filled with them. They occur in the dense, warm gas surrounding newborn stars inside molecular clouds. Molecules like water vapor or methanol, energized by the star's fierce radiation, act as a cosmic amplifier. They don't just glow randomly, they emit radiation in perfect lockstep, creating an intense, narrow beam of pure microwave or radio light. Think of it like a crowd whispering, and then suddenly, through a chain reaction, every single person whispers the same word at the exact same moment, creating a single, powerful voice that carries for miles. That is the coherent power of a maser. We find them often, and they are brilliant tools for mapping the violent outflows from infant suns. But sometimes, the maser's song is a little too perfect, a little too strange. Astronomers point their dishes at these natural lasers and detect emission with a level of coherence and polarization that defies the standard textbook model. The light is too orderly, too clean. It is as if you expected the whispering crowd to produce a clear word, but instead they recited a perfect, synchronized poem in a language you barely recognize. This extreme coherence points to an environment of almost unimaginable violence and precision. The current models of stimulated emission in water or methanol molecules rely on specific densities, temperatures, and levels of turbulence. They work for most masers. But these anomalous signals suggest something far more extreme is at play within the heart of the cloud. One possibility is that we are looking into a region of hyperturbulence, where shock waves from the newborn star are ripping through the gas at incredible speeds, creating conditions so chaotic that they somehow force the molecules into an even more uniform, synchronized state. It is a paradox where extreme disorder begets extreme order. Another, even more compelling idea involves magnetic fields of monstrous strength. Molecular clouds are threaded with magnetism, but in the cores where massive stars form, these fields can be amplified to staggering intensities. A supremely powerful, highly ordered magnetic field could act like a cosmic conductor's baton, forcing the energized molecules to align and sing in perfect phase and polarity. The maser emission we see would then be a direct map of magnetic field lines wound tighter than we thought possible, revealing a hidden, ferocious structure within the apparent chaos of the nursery. These coherent maser hotspots are more than just bright beacons. They are probes, sending us a signal that encodes the most extreme of physics occurring in the secret hearts of stellar birthplaces. They tell us that our models of these clouds are still too tame, that the reality inside is a realm of perfect storms and invisible, ordering forces of immense power, writing their signature in beams of unnaturally pure light. The unnaturally coherent light of a maser reveals a hidden order within the chaos, but some clouds broadcast a far more violent and energetic secret. Across the galaxy, orbiting telescopes like the Fermi Large Area Telescope scan the heavens not for radio whispers, but for gamma rays, the most powerful form of light in the universe. These photons carry the signature of the cosmos's most extreme events: supernova explosions, pulsar winds, and black hole jets. Yet, when Fermi maps the gamma-ray sky, it finds bright, diffuse patches of this high-energy light that overlap perfectly with the locations of dark, quiescent molecular clouds. This is a profound contradiction. These clouds are cold, dense, and seemingly inert, the last places you would expect to generate gamma radiation. There is no visible supernova remnant at the heart of the glow, no spinning pulsar beacon. The source of the violence is completely hidden, giving rise to the compelling mystery of the dark accelerators. The leading hypothesis to explain these cloud-encased gamma-ray sources involves the relentless rain of cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, accelerated to nearly the speed of light by distant cataclysms. Picture the molecular cloud as a massive, floating target in a galactic shooting gallery. When these ultra-fast cosmic ray protons, arriving from some unseen source far away, slam into the slow-moving protons of the hydrogen gas inside the cloud, they can create a shower of secondary particles, including neutral pions, which almost instantly decay into pairs of gamma rays. In this scenario, the cloud is not the accelerator, it is merely the luminous screen where a distant drama makes its impact visible. The gamma-ray glow is the flash of light from each cosmic ray bullet striking the target. This would mean the cloud is acting as a giant particle detector, revealing the presence and intensity of a cosmic ray bombardment whose origin we must trace elsewhere. But there is a second, even more intriguing possibility: the dark accelerator model. What if the particle acceleration is happening inside the cloud itself? The molecular cloud, with its complex magnetic fields and turbulent motions, could be hiding a natural particle collider. Shocks from powerful stellar winds of hidden, massive stars could be propagating through the dense gas, accelerating particles directly. Or perhaps a population of young, energetic stars, still deeply embedded in their dusty cocoons and invisible to our optical telescopes, are producing fierce outflows that collide and create shock fronts capable of boosting particles to extreme energies. In this case, the gamma rays are not from an external bombardment, but from a local, internal violence, a storm raging inside the cloud that we cannot directly see. The cloud is both the accelerator and the target. The enigma forces us to question the very nature of these dark nurseries. Are they passive reservoirs of gas, or are they active, energetic engines in their own right? Each unexplained gamma-ray glow is a signpost pointing to a hidden forge of cosmic power. It challenges us to look past the apparent calm of the dust and see the potential for immense, concealed forces at work, where the birth of stars might be accompanied by the secret acceleration of matter to nearly the speed of light, painting the darkness with a faint, deadly shine we are only beginning to interpret. These gamma-ray glows paint a picture of violent energy, but deep in the hearts of the clouds, another kind of change unfolds with a startling speed. Astronomers have trained their most sensitive instruments on the dense cores within molecular clouds, the very cradles where individual stars begin their collapse. They expect to see a slow, stately process, a gravitational sinking that takes tens of thousands of years. Instead, they watch the light from these cores flicker. In the submillimeter and radio waves emitted by cold dust and gas, the brightness of some dense cores changes measurably over mere months or years. This is the unexplained time variability in cloud cores, a phenomenon that moves at a pace far too swift for the standard, plodding story of star birth. Imagine watching a time-lapse of a glacier carving an iceberg, but instead of a slow, majestic break, you see the ice shudder and flash with rapid bursts of motion. That is the scale of the mismatch. The cloud's heart is beating, and we do not know why. One of the most compelling explanations points to a hidden infant star, a protostar, buried so deeply in its dusty womb that its visible light cannot escape. Even in its infancy, this protostar might not feed steadily. It could experience violent, episodic accretion bursts. Imagine a logjam in the river of gas flowing on to the young star. Pressure builds until suddenly, catastrophically, the dam breaks, and a torrent of material crashes onto the protostar's surface in a matter of months. This sudden injection of mass releases a surge of energy that heats the surrounding dust in the core, causing its submillimeter glow to brighten sharply before fading again as the flow stabilizes. We would not see the star, but we would see its dusty cradle suddenly flare in the heat of its feast. Another possibility involves the invisible architecture of magnetic fields threading the core. These fields can become twisted and strained as the gas moves. Occasionally, they may snap and reconfigure in a violent event called magnetic reconnection, a process that can release tremendous energy in a short time, like a cosmic circuit breaker exploding. This sudden release could briefly heat the local dust or excite molecules, causing a temporary brightening in the core's radio signature before everything settles into a new, slightly different magnetic configuration. Perhaps the simplest, yet most elusive idea is that we are not seeing a change in brightness, but a change in shadow. The internal structure of a dense core is not smooth. It is a complex web of filaments and clumps. If a particularly dense knot of gas and dust drifts across our line of sight, it could act as a moving veil, momentarily blocking or scattering the background emission from the rest of the core, making it appear to dim from our vantage point. The flicker would then be a shadow play on a cosmic scale, a dark puppet moving within the cloud's heart. Each of these explanations reveals a dynamic, almost frenetic reality inside what we thought were serene stellar nurseries. The slow, grand narrative of gravitational collapse is punctuated by rapid, energetic chapters, secret feasts, magnetic snaps, and drifting shadows. This variability is a signal that star formation is not a smooth, continuous process, but a story told in fits and starts, with its most crucial moments hidden behind curtains of dust, revealing themselves only as subtle, mysterious flickers in the cold dark. Deep within the flickering hearts of cloud cores, the story grows colder and denser still. Beyond the familiar dark nebulae lie even more extreme structures, known as infrared dark clouds. These are the ultimate cosmic freezers, so thick with dust that they blot out not just visible starlight, but even the background glow of infrared warmth from the galaxy itself. They appear as absolute black silhouettes against the infrared sky, frigid vaults where gravity is just beginning to muster its strength, the very precursors to the most massive stars in the galaxy. And within these silent, frozen fortresses, radio telescopes have picked up something that should not exist. They are called cold radio bursts, fleeting spikes of emission from regions where no star has yet ignited, where the temperature is barely 10 degrees above absolute zero. It is like hearing a sudden, sharp crack from deep inside a glacier, a sound with no visible source. The very existence of these bursts is a paradox. Radio emission typically requires energy, heat, or violent motion, all things a prestellar core in an infrared dark cloud should lack. So what could possibly cause a blast of radio waves in a place that is essentially a uniform, freezing cold ball of gas and dust? One electrifying theory points to a phenomenon we know all too well on Earth: static discharge. Inside these ultra-dense clouds, dust grains are constantly bumping and rubbing together. In that near-perfect vacuum, electrons can be scraped off one grain and transferred to another, building up immense electrical charges over vast scales. Picture the entire core of a cloud, light years across, acting like a single, gigantic capacitor. The tension builds until the insulating properties of the cold gas itself breaks down, and a titanic spark leaps across the void. This would not be lightning as we see it, with a visible plasma channel, but a sudden, colossal discharge of static electricity, releasing its energy as a burst of radio noise. It would be the universe's largest thunderclap, occurring in utter silence and darkness. Another possibility is even more foundational. These infrared dark clouds are on the very brink of collapse. Their magnetic fields are wound incredibly tight, fighting a desperate battle against gravity. Theorists suggest that just before the core gives way and a star begins to form, the magnetic field may reach a breaking point. Lines of force could snap and reconfigure in a catastrophic event of magnetic reconnection, releasing a concentrated blast of energy that ripples through the surrounding gas as a radio burst. This signal would be the death cry of the magnetic field's resistance, the moment the cloud's internal structure fails and commits to the birth of a behemoth star. These cold bursts are perhaps the most pristine signals of all, untouched by the violence of stellar youth. They are the tremors that come before the earthquake, the first faint crack in the dam of a molecular cloud. Each one is a herald, a signal from the deepest cold announcing that in the absolute stillness, forces are aligning for a creation of immense power. The cold radio bursts are the first tremors of creation, but the chemistry within these frozen vaults holds a quieter, more intricate mystery. Deep in the heart of a molecular cloud, where temperatures plunge near absolute zero, a subtle atomic swap is taking place. Hydrogen, the simplest and lightest element, has a heavier twin called deuterium. It is an isotope, meaning its nucleus contains a neutron alongside the proton, making it roughly twice as heavy. In the vast, warm expanse of interstellar space, deuterium is exceedingly rare. But inside the cold molecular clouds, something extraordinary happens. Molecules like formaldehyde, ammonia, and water ice are found with deuterium atoms swapped in for their regular hydrogen at levels hundreds or even thousands of times higher than the cosmic average. This process, called fractionation, is a well-known chemical signature of extreme cold. The physics is elegant. Heavier deuterium binds slightly more tightly to other atoms than regular hydrogen does in the frigid environment, giving it a minute chemical advantage that snowballs over time. So finding deuterium-rich molecules is not the mystery. The puzzle lies in the pattern. When astronomers map the deuterium fractionation across different molecules in different parts of a cloud, the observed ratios often defy the predictions of our best ion molecule chemistry models. It is as if you entered a bakery expecting a specific ratio of sugar to flour in every recipe, but instead you find wildly different, inconsistent sweetness levels in the bread, the cakes, and the cookies, with no clear reason why. The models, which account for temperature, density, and the basic rules of atomic interaction in the dark, should produce a predictable chemical fingerprint. Yet the clouds are writing a more complex story. One leading suspect is the strange, sticky world of interstellar ice. In the ultra-cold, atoms and molecules do not simply float and collide in gas. They freeze onto the surfaces of microscopic dust grains, forming icy mantles. These are not simple sheets of ice, but complex, porous structures, likely laced with exotic compounds. The sticking probability of a deuterium atom versus a hydrogen atom on these bizarre, cosmic ice surfaces is a complete unknown. If deuterium sticks more efficiently, or if it can tunnel through quantum mechanical barriers in the ice that regular hydrogen cannot, it would be preferentially incorporated into molecules forming on those grains, skewing the ratios in ways our gas phase-only models cannot predict. Another variable is the invisible rain of cosmic rays. These high-energy particles are the primary drivers of chemistry in the dark, ionizing molecules and kicking off chains of reactions. But the flux of cosmic rays penetrating a cloud is not constant. It can vary based on the cloud's depth, its magnetic field structure, and even recent nearby supernovae. A slight change in this ionizing radiation would dramatically alter the chemical pathways, potentially enhancing deuterium fractionation in some molecules while leaving others untouched. The anomalous patterns are therefore a chemical fossil record, a snapshot of a cloud's hidden history, its exposure to radiation, the unique properties of its dust, and the quantum mechanical quirks playing out on frozen specks smaller than a wavelength of light. To decode it is to read the detailed diary of a cloud's internal life, written not in words, but in the subtle, heavy signature of a rare atomic twin. Deuterium fractionation reveals the subtle quantum diaries of a cloud's internal life, but sometimes a cloud delivers a message of staggering complexity, one that seems to speak directly to the building blocks of life itself. In the tumultuous star-forming region known as Sagittarius B2, a massive cloud near the center of our galaxy, radio telescopes made an astonishing detection. They found the spectral signature of a molecule called propylene oxide. On its own, finding a complex organic molecule in space is thrilling, a sign of the sophisticated chemistry these dark nurseries can perform. But this discovery held an even deeper twist. The propylene oxide molecules exhibited a property known as chirality, or handedness. This means the molecule comes in two distinct forms that are mirror images of each other, like your left and right hands. You can try to superimpose them, but they will never match perfectly. This handedness is not just a chemical curiosity, it is a fundamental feature of life as we know it. Every living organism on Earth uses amino acids of one specific handedness, left-handed, and sugars of the opposite, right-handed handedness. This uniform preference is what allows complex biological structures, like the double helix of DNA, to assemble with precision. Life is built on molecules that have chosen a side. So the detection of a chiral molecule in a star-forming cloud is profound. It means the raw ingredients for life are not only being manufactured in the cold depths of space, but they are being forged with the very architectural property that life requires. The immediate, electrifying question is, why? Is the handedness we see in Sagittarius B2 random, a roughly equal mix of left and right-handed molecules swirled into the cloud? Or is there a physical process in the cloud itself that favors one hand over the other? The leading theory points to a subtle but powerful force, circularly polarized light. Near the furious young stars being born in Sagittarius B2, intense magnetic fields can twist starlight, causing it to spiral as it travels. This circularly polarized light could selectively break down one form of the chiral molecule slightly more than its mirror image, leaving behind a slight excess of the other. It would be a cosmic filter, subtly biasing the chemistry before it ever reaches a planet. If this is the case, then the molecular clouds are not just factories. They are quality control stations imprinted with a subtle bias that could seed an entire galaxy with a preferred handedness. The alternative is that the handedness is random in the cloud, and the selection happens later on the surface of a young planet through purely local chemical processes. But the very presence of chiral molecules in the cloud forces us to confront an awe-inspiring possibility. The propensity for life, the very architectural preference that defines its complexity, may not be a happy accident on a warm, wet world. It might be written into the universe's recipe from the very beginning, in the cold, dark cradles where stars and planets are born. The signal from Sagittarius B2 is more than a spectral line. It is a whisper about destiny, suggesting that the path to life might be illuminated, ever so faintly, by the twisted light of newborn suns. The chiral whispers from Sagittarius B2 speak to the potential for life's architecture, but some clouds cloak themselves in structures of pure energy, visible only as a faint, all-encompassing glow. Across the galaxy, radio telescopes mapping large molecular complexes like the California Cloud, a massive star-forming region in the constellation Perseus, have detected something strange enveloping the entire structure. It is not a point source or a bright maser spot. It is a faint, diffuse radio halo, a soft shell of emission that seems to cocoon the cloud itself, extending far beyond its dense, dusty heart. This is not the sharp, focused light of a natural laser, but the gentle, pervasive sigh of something energetic happening on a colossal scale. The known processes fail to fully explain it. Synchrotron radiation, the emission given off when high-energy electrons spiral around magnetic field lines, is a prime suspect. But the halo's characteristics, its specific frequencies and its smooth distribution do not perfectly match the signature expected from the known population of galactic cosmic ray electrons. It is as if you found a city surrounded by a uniform, dim light, but the known street lamps and car headlights cannot account for its soft, even glow. So what is illuminating the cloud's outer atmosphere? One compelling idea involves a hidden population of low-energy cosmic rays, protons and electrons that are too sluggish to create the brilliant flashes we associate with their high-energy cousins. The molecular cloud, with its complex magnetic field, could act as a gigantic magnetic bottle, trapping these slower particles within its grasp. As these trapped particles slowly spiral along the cloud's vast magnetic field lines, they would emit a faint, diffuse radio whisper, painting the entire structure with a soft halo of their presence. The cloud becomes its own lantern, powered by a captive sea of low-energy particles we normally cannot detect. Another fascinating possibility points to the cloud itself, vibrating like a colossal drumhead. Within the magnetized plasma of the cloud's outer layers, immense waves called alpha-N waves can propagate. These are not sound waves or water waves, but ripples in the magnetic field itself, set in motion by the turbulent motions of the galaxy or by the violent births of stars within the cloud. As these magneto-hydrodynamic waves travel through the cloud's diffuse outskirts, they can transfer energy, gently heating the thin gas and causing it to emit the observed radio halo. Think of it as the cloud ringing out at a very low, deep frequency, and the radio halo is the visible shimmer of that slow, majestic vibration. This explanation ties the cloud's large-scale structure directly to the dynamic forces of the galaxy, suggesting these nurseries are not isolated islands, but are constantly being stirred and energized by the cosmos around them. The unexplained radio halo is therefore a signature of connection. It reveals the cloud not as a passive, cold lump, but as an active participant in the galactic ecosystem, either humming with trapped particles or resonating with the deep magnetic songs of the Milky Way. It is a reminder that sometimes the most profound signal is not a shout from the center, but the soft, encompassing breath of an entire structure, whispering secrets about the hidden energy that binds it to the universe. That soft, encompassing halo reveals a cloud connected to the galaxy, but some signals defy connection entirely, emerging from the deepest voids. We have met the chattering, repeating fast radio bursts with their 16-day rhythms, but they represent only one side of the phenomenon. The vast majority of fast radio bursts are one-time events, brilliant cosmic gunshots that fire once and are never heard from again. Astronomers call these the non-repeating or silent fast radio bursts. Their mystery is compounded by a new and startling observation. When we manage to pinpoint the location of one of these singular flashes, we sometimes find nothing at all. No glowing host galaxy, no lingering afterglow in any other wavelength of light, just an empty patch of sky. It is as if a firecracker exploded in a completely dark room, leaving not even a wisp of smoke to show where it had been. This absence is as provocative as any signal. If these colossal explosions, which can release more energy than our sun puts out in a century, are not tied to any galaxy we can see, where are they coming from? One compelling and haunting theory points to the darkest, most isolated places imaginable, rogue molecular clouds adrift in intergalactic space. Picture a massive cloud of gas and dust, billions of times the mass of our sun, that has been violently torn from its home galaxy during a cosmic collision or ejected by gravitational forces. This colossal structure now drifts alone in the immense, empty black between galaxies, a ghost ship on a sea of nothing. Within this isolated cloud, the normal, slow process of star birth could still occur, but in total secrecy, far from the light of any galactic city. In such a place, a cataclysm could unfold unseen. Two neutron stars, the ultra-dense remnants of dead suns, could spiral together and merge in a titanic collision, their final moments unleashing the fast radio burst. Or a wandering black hole could encounter a particularly dense knot of gas within the cloud, consuming it in a sudden, violent feast that sends out a flash of radio waves as its final signature. The event would be brilliant, but its context would be absolute darkness. The surrounding cloud, cold and devoid of stars, would offer no persistent glow, no galaxy to host the event. It would be a tragedy staged on an empty set, witnessed only by the fleeting signal it produced. This idea transforms our understanding of these silent bursts. They may not be messages from the stellar nurseries of galaxies, but death cries from the universe's loneliest places, from orphaned clouds where matter gathers and dies in profound isolation. It suggests that the ingredients for these spectacular explosions are not confined to galaxies, but are scattered throughout the cosmic voids, hidden within drifting islands of darkness. The next time a silent, fast radio burst flashes and vanishes, we must ask, are we hearing the last sound of something dying in the deepest dark? A signal from a place that belongs to no one and nowhere. These silent bursts vanish into the apparent emptiness between galaxies, but within the clouds themselves, the very fabric of matter holds a more subtle, rhythmic secret. Recent wide-area surveys mapping molecular clouds in sub-millimeter light, which sees the cold glow of dust itself, have unveiled an astonishingly delicate architecture. The clouds are not just blobs, They are intricate tapestries of wispy filaments, long strands of gas and dust stretching for light years like cosmic threads. And along the lengths of these filaments, astronomers are finding something strange, periodic density variations that look like gentle, regular wiggles. It is as if you were looking at a gargantuan violin string frozen in space and could see a perfect standing wave vibrating along its entire length. These sub-millimeter wiggles are a new kind of cosmic rhythm, and their origin is a captivating puzzle. One of the leading explanations is profoundly beautiful. These could be interstellar sound waves. In the thin, magnetized plasma of a molecular cloud, pressure waves can indeed travel, but they are not sounds we could hear. They are oscillations moving at hundreds of thousands of miles per hour, compressing and rarefying the gas as they go. If a filament is hit by a shock wave from a distant supernova or stirred by the turbulent birth of a nearby star, it could begin to vibrate at its natural resonant frequency, creating those regular, spaced-out, denser regions we see as wiggles. The filament would be singing a deep, ultrasonic note, and the wiggles are the visual record of its song. Another possibility ties the structure to the cloud's invisible magnetic skeleton. The filaments are known to form along the lines of interstellar magnetic fields. An instability in that magnetic field, like a kink instability where the field lines twist and buckle under pressure, could periodically pinch the gas, creating the observed pattern of dense beads along a string. The wiggles would then be a fossil imprint of a magnetic struggle, a snapshot of the field's structure at the moment the filament froze into existence. But there is a third, far more speculative idea that pushes the mystery into the realm of the truly unknown. What if the wiggles are not caused by anything within the cloud at all? What if they are an imprint, a gravitational scar left by something invisible passing through? Streams of dark matter, the mysterious substance that makes up most of the mass in the universe, but does not interact with light, are theorized to flow through galaxies like ours. If a dense stream of this dark matter were to pass through a molecular filament, its gravity could subtly tug on the gas, pulling it into a series of clumps along the stream's path. The wiggles would be a ghostly footprint, the only visible sign that an invisible river of unknown matter had recently flowed through the stellar nursery. While this dark matter hypothesis is highly speculative, it illustrates the profound potential of these delicate structures. They are not just pretty patterns. They are high-precision records of the forces acting on the cloud, whether they are the familiar pressures of sound and magnetism or the elusive whisper of the universe's dominant but hidden component. Each gentle wiggle in the data is a question written in dust and cold gas, asking us to listen for the deepest vibrations of the cosmos. Those delicate wiggles in the filaments are a record of hidden forces, but one dark cloud is so close we can see its silhouette with our own eyes. On a clear southern night, you can look toward the constellation Crux, the Southern Cross, and see a patch of sky where the stars seem to vanish. This is the Coalsack Nebula, a vast dark cloud of gas and dust just 600 light-years away, a sooty smudge against the brilliance of the Milky Way. It is the most prominent dark nebula in our sky, a neighbor in the cosmic sense, and its proximity makes it a perfect laboratory. When radio astronomers trained their most sensitive arrays on the Coalsack, they were not looking for brilliant flashes. They were listening for the quietest possible whispers. And they heard something. From the cloud's densest, coldest heart came an extremely faint, narrow-band radio signal. It was not static or noise, but a coherent-sounding whisper, a tone so pure and faint it seemed almost artificial. The signal's very existence in such a cold, starless environment is the first part of the mystery. The Coalsack is not a star-forming factory like Orion. It is a quiet, cold reservoir. So what could possibly generate a coherent radio whisper in a frozen vault? The first and most likely explanation is frustratingly mundane, reflected terrestrial interference. our planet is awash in human-made radio noise, from television broadcasts to radar. Some of this energy leaks into space and can bounce off the ionized layers of our own atmosphere, or even off the moon, and be reflected back toward Earth, where a sensitive telescope might pick it up as a faint, seemingly celestial signal. The coal sack, sitting in a busy part of the radio sky, could simply be acting as a silent backdrop against which we see the ghost of our own chatter. Yet, the signal's specific characteristics have prompted scientists to explore possibilities that venture far beyond human technology. One of the most profound exotic explanations involves a hunt for the universe's most elusive substance, dark matter. Theorists have proposed that dark matter could be made of hypothetical particles called axions. These are ultra-light particles, billions of times lighter than an electron, that were conceived to solve a deep problem in particle physics. In the presence of a strong magnetic field, such as those threading through a dense molecular cloud like the coal sack, axions could theoretically convert into ordinary photons, particles of light, specifically radio waves. The process would be incredibly rare and faint, but across the vast volume of a dark cloud, it could produce just the kind of faint, coherent whisper that has been detected. The coal sack, with its strong internal magnetic fields and its lack of confusing stellar engines, becomes an ideal natural detector for this phantom particle. A confirmed signal from axion decay would be a monumental discovery, finally revealing the nature of the invisible matter that holds galaxies together. So the whisper from the coal sack presents us with a stark choice. Is it merely an echo of ourselves, a faint reflection of our own radio noise bouncing back from a cosmic wall? Or is it the first faint radio voice of dark matter itself, a particle that is hidden from us since the beginning of time, finally announcing its presence from the darkness next door? This nearby cloud, a familiar silhouette in the night, may be holding a secret that divides our understanding of the universe into before and after. The whisper from the coal sack presents a stark choice between an echo of ourselves and a voice from the void, but other clouds communicate through a silent, contradictory language of absence and presence. Deep within certain molecular complexes, astronomers map the structure using different molecular tracers, essentially taking the cloud's temperature and density with different chemical thermometers. They expect a consistent story. Where the cloud is densest and coldest, as shown by one tracer, the emission from another common molecule, like carbon monoxide, should also be strong. But in some regions, the data tells a bafflingly opposite tale. As the signal from the dense gas tracers grows stronger, indicating a knot of material ripe for star formation, the expected glow from carbon monoxide unexpectedly fades away. This is the unexplained anti-correlation, a technical term for a simple, profound contradiction. The cloud seems to be missing something precisely where it should be most abundant. It is as if you were walking through a forest, and the deeper you went into the thickest grove of trees, the fewer bird songs you heard, defying all logic of where life should thrive. This silent patch within the noisy heart of a cloud points to a fundamental gap in our models. Carbon monoxide is the second most abundant molecule in space after hydrogen, and for decades it has been the workhorse for mapping molecular clouds. Its sudden disappearance in the densest cores is not just a missing data point, it is a clue that the environment there is doing something to the carbon monoxide that our textbooks did not predict. One of the leading suspects is an ultra-efficient freeze-out process. We know that in the extreme cold, molecules can stick to the surfaces of dust grains, forming icy mantles. But perhaps in these specific cores, the conditions are so perfectly cold and dense that carbon monoxide freezes onto the dust grains with near 100% efficiency, almost instantly. The molecules are not gone, they are simply locked away in a frozen prison, invisible to our radio telescopes that only see the gas phase. The dense gas tracer, perhaps a rarer molecule that resists freezing, continues to shine, highlighting the core's location while the carbon monoxide glow winks out, creating the anti-correlation. It is a cosmic game of hide-and-seek, where the most common player is the best at hiding. But freeze-out is not the only possible thief. The violent dynamics of a cloud's heart could be responsible. If a particularly powerful shock wave, perhaps from a nearby protostellar jet, is plowing through the dense core, it could do more than just heat the gas. It could literally tear the carbon monoxide molecules apart. The intense energy of the shock could dissociate them, breaking the carbon-oxygen bonds before the molecules have a chance to reform and emit their characteristic signal. In this scenario, the dense gas tracer might be a hardier molecule that survives the shock, leaving it as the sole witness to the core's density after the carbon monoxide has been destroyed. The anti-correlation becomes a fossil record of a recent cataclysm, a shock front's path etched in missing light. A third, more subtle possibility involves light from outside the cloud itself. While molecular cloud cores are famously dark, they are not perfectly sealed. Fierce, ultraviolet radiation from distant, massive stars can penetrate the cloud's outer layers, creating what astronomers call photon-dominated regions, complex chemical zones where the high-energy light fundamentally alters the chemistry. Deeper inside, the radiation fades, allowing different chemistry to take over. The anti-correlation could be a map of this transition, a sign that we are seeing a boundary layer where one type of chemical regime is giving way to another. The carbon monoxide might be chemically transformed into other carbon-bearing species like carbon dioxide or complex organics in this irradiated boundary, causing its signal to drop just as the density increases. This would mean the cloud is not a uniform chemical vat, but a layered, dynamic arena where external forces write complex patterns in molecular light and shadow. Each of these explanations, from perfect freezing to destructive shocks to penetrating starlight, reveals that the simple maps we first make of these clouds are just sketches. The true picture is a three-dimensional puzzle of physics and chemistry, where the absence of a signal can shout just as loudly as its presence, telling a story of hidden reservoirs, violent histories, and invisible borders drawn by light from stars we cannot even see. The silent patches where carbon monoxide vanishes tell us that maps of clouds are incomplete. But what happens when the map itself points to a cataclysm that never should have happened there? This brings us to one of the most disorienting cosmic mismatches, the search for the orphaned gamma-ray burst. Gamma-ray bursts are the single most violent explosions in the universe since the Big Bang. For a few fleeting seconds, they outshine entire galaxies, releasing more energy than our Sun will in its entire 10 billion-year lifetime. The long-duration bursts, those lasting more than 2 seconds, are confidently linked to the death of a very specific kind of star, a massive, rapidly spinning star with low metallicity, meaning it lacks heavy elements. When such a star exhausts its fuel, its core collapses directly into a black hole, powering a jet of material that punches through the star's outer layers at nearly the speed of light. That jet, pointed directly at Earth, is what we see as a brilliant gamma-ray burst. So when we detect one of these titanic flashes, astronomers immediately race to pinpoint its location and look for its host galaxy, the stellar nursery where its progenitor star was born. And sometimes they find something deeply confusing. The afterglow of the burst points not to a bright star-forming spiral or irregular galaxy, but to a seemingly quiet, quiescent molecular cloud complex, a dark and dusty structure with no signs of recent, vigorous, massive star formation. It is like finding the smoldering crater of a volcanic explosion in the middle of a calm, frozen tundra, where no volcano has existed for millions of years. How can the universe's most violent stellar death occur in a place that shows no evidence of ever birthing such a star? The leading theory to resolve this paradox is as dramatic as the burst itself: the runaway star. Imagine a binary star system born deep within the turbulent heart of a massive molecular cloud. Both stars are massive, but one is slightly more so. When the more massive star exhausts its fuel and explodes as a supernova, the explosion can be asymmetrical, kicking the surviving companion star like a cosmic cannonball. This surviving star, already massive and spinning fast, is ejected from its birthplace at incredible speed, hundreds of thousands of miles per hour. It becomes a runaway, a stellar fugitive blazing a solitary path through the galaxy. This star travels for millions of years, carrying the seed of its own spectacular demise within it. By the time its own core finally collapses and triggers a gamma-ray burst, it has traveled far, far away from its original stellar nursery. It may now be passing through, or even on the outskirts of, a completely different, quiet molecular cloud. From our vantage point, the brilliant flash appears to be located within that peaceful cloud, but the cloud is merely an innocent bystander, a dark backdrop against which the runaway star's final act plays out. The progenitor was a visitor, not a native. But there is another, even more intriguing possibility. What if the quiet cloud itself is the true birthplace? This forces astronomers to consider a new, unknown mechanism for gamma-ray burst production. Perhaps in certain pristine, low metallicity pockets within these vast clouds, the process of star formation can occasionally forge a massive star with the perfect, rare characteristics for a gamma-ray burst through a pathway we have not yet modeled. Maybe the star formed in such isolation and with such a unique magnetic field structure that it left no visible cluster or bright nebula as a calling card, living and dying in near total secrecy within the cloud's opaque depths. The cloud itself, then, would be a host to a rare and invisible type of stellar factory, one that produces cosmic bombs without the usual fireworks of a stellar nursery. The orphan gamma-ray burst, seemingly parentless in a quiet cloud, challenges our neat narratives of cause and effect. It forces us to consider the lives of stars as journeys where an object can die far from its home, or it suggests that the dark clouds hold secrets about stellar birth we are only glimpsing in the aftermath of their most violent ends. The flash is not the end of the story, but the beginning of a deeper mystery, a question written in gamma rays against a dark and silent sky. The most profound cosmic deceptions are not whispers from the void, but perfect imitations of intelligence. For decades, the search for extraterrestrial intelligence has been guided by a simple principle: look for a signal that cannot be explained by nature. The ideal candidate is a narrowband radio transmission, a pure, unwavering tone like a cosmic whistle, because natural astrophysical processes tend to be messy, emitting across a wide range of frequencies. So when such a pristine signal was detected emanating from a region in the constellation Cygnus, centered on a dense molecular cloud core known for its furious star formation, excitement was palpable. It was a perfect, narrow-band radio whistle, seemingly broadcasting from a stellar nursery. The signal, catalogued as SHC2465, had all the hallmarks of a techno-signature, a beacon. Yet, upon deeper investigation, a far more fascinating natural explanation emerged. The source was not a civilization, but a violent young stellar object, a protostar still swaddled in its dusty cocoon. This infant sun was spewing out vast jets of charged particles, creating a turbulent plasma around it. Within this plasma, a phenomenon known as an electron-cyclotron-Mesa instability was occurring. As electrons spiraled along the protostar's powerful magnetic field lines, they were forced to emit radiation at one precise frequency, creating that artificial-sounding, narrow-band whistle. It was a natural radio laser, a product of raw stellar infancy, perfectly mimicking the signature we had assigned to advanced technology. This is not an isolated case. Another celebrated example came from observations of the famous Orion Molecular Cloud. A signal detected there exhibited not just a narrow bandwidth, but a slow, rhythmic pulse, a kind of modulation that again sparked speculation. The pulse period was too regular for many known variable stars, and its location deep within the cloud made it seem mysterious. The culprit, however, was a dazzling interplay of physics and geometry. The signal's source was a distant, rapidly spinning pulsar, the ultra-dense remnant of a supernova. Its lighthouse-like beam of radio waves was not pointed directly at Earth. Instead, it was aimed toward the vast, turbulent veil of the Orion cloud. As the pulsar's beam passed through the cloud's shifting layers of ionized gas, the material acted as a celestial lens, intermittently focusing and defocusing the signal. From our vantage point, this created the illusion of a slow, deliberate pulse superimposed on the pulsar's own rapid spin. The cloud itself was a giant dynamic filter, sculpting the pulsar's natural signal into a pattern that, to our eager algorithms, looked intentionally crafted. These episodes serve as a humbling and crucial lesson in cosmic epistemology. They reveal that the cold, chaotic nurseries of stars are not just factories for matter, but for signals that can pass every test for artificiality we can devise. Plasma instabilities around young stars can generate purity from chaos. The scintillation of pulsar light through drifting cloud material can impose order and rhythm. The universe, in its boundless complexity, possesses a toolkit for creating patterns that our limited experience interprets as design. This does not diminish the search, it refines it. It forces us to ask more sophisticated questions, to listen not just for a signal that seems intelligent, but for one that persists in its intelligence across every conceivable natural explanation. The clouds, in their brilliant mimicry, have taught us that the line between a natural phenomenon and a message might be thinner than a wavelength of light, written in the very processes that build stars and planets. From the deceptive mimicry of intelligence, we turn to a signal that is unmistakably real, a ghostly light born from the destruction of matter itself. Near the heart of our galaxy, a persistent, eerie glow has been mapped across the sky, a specific type of gamma-ray light with an energy of 511,000 electron volts. This is not just another cosmic emission. This is the fingerprint of annihilation. When an electron meets its antimatter twin, a positron, they destroy each other in a flash of pure energy, producing gamma rays at this exact, precise wavelength. The sky is lit up with this ghost light, and its brightest, most intense source is the chaotic region surrounding the supermassive black hole at the galactic center. Astronomers have nicknamed this region the Great Annihilator. But the mystery deepens when you look at the map. This annihilation glow is not confined to a single point. It is diffuse, spreading out across the central bulge of the Milky Way. And crucially, it overlaps with some of the galaxy's most massive and turbulent molecular cloud complexes, like the sprawling Sagittarius B2 cloud. This presents a profound cosmic whodunit. Where are all these positrons coming from, and what role do the dark, dusty clouds play in their final, luminous destruction? One leading theory casts the molecular clouds as passive cosmic sponges. In this scenario, the primary positron factory is something powerful at the very center of the galaxy, perhaps material violently churning around the supermassive black hole itself, or a dense cluster of exotic stellar remnants like pulsars and magnetars. These central engines would blast positrons out into the galactic environment at nearly the speed of light. These antimatter particles would then travel for hundreds or thousands of light years before finally encountering the dense walls of a giant molecular cloud. Slamming into the cloud's thick hydrogen gas, a positron would quickly meet an electron and in a final flash of 511,000 electron-volt light, be annihilated. The cloud, in this view, is merely a luminous screen, a dark canvas that lights up wherever the antimatter bullets from the center happen to strike. It tells us where the positrons are dying, but not where they were born. But there is a competing and far more intriguing possibility. What if the clouds are not just absorbers, but generators? Could these stellar nurseries be creating antimatter within their own dark hearts? The environment inside a massive cloud complex is far from tranquil. It is a cauldron of high-energy processes. Intense radiation from newly formed massive stars can generate particle showers. Shocks from colliding gas streams or protostellar jets could accelerate particles to energies where positron production becomes possible. There could even be a population of unusual, hidden stellar corpses within the clouds, like soft gamma-ray repeaters, whose powerful magnetic fields are capable of spawning electron-positron pairs. In this scenario, the annihilation glow is local. The cloud is both the factory and the killing floor for antimatter, its diffuse light a sign of violent physics playing out in the secret depths of stellar birth. Perhaps the most speculative idea pushes the mystery into the realm of the truly exotic. Some theorists have proposed that the positrons could be the signature of dark matter particles annihilating with one another. If dark matter is made of certain types of hypothetical particles, their mutual annihilation could produce electron-positron pairs as a direct byproduct. Dense molecular clouds, with their strong gravitational pull, could act as natural traps, concentrating dark matter and making these annihilations more frequent and visible. The 511,000 electron volt glow from clouds like Sagittarius B2 would then be an indirect signal of the universe's most elusive substance, a ghostly light produced by ghosts. The great annihilator's true identity remains hidden, its signals smeared across the dark clouds that either absorb its output or generate their own. This antimatter glow is a cosmic question written in the most fundamental language of physics, a question about where matter goes to die and whether the darkest places in the galaxy are quietly, brilliantly engaged in the work of creation and destruction on a subatomic scale. That ghostly antimatter glow speaks of destruction at a subatomic scale, but within the clouds, another signal twists light itself into a spiral of mystery. We have already encountered astrophysical misers, those natural lasers that beam coherent whispers from stellar nurseries. Their light is often polarized, meaning its waves vibrate in a preferred direction, usually aligned with the magnetic fields threading the cloud. This linear polarization is a powerful tool, letting astronomers map the invisible magnetic skeleton of star birth. But a handful of these masers do something far stranger. They emit light that is strongly circularly polarized. Instead of vibrating in a flat plane, the electric field of the light rotates as it travels, spiraling through space like a corkscrew. This intense circular polarization is exceptionally rare and extraordinarily difficult for nature to produce under normal conditions. It is a signature of an environment pushed to an extreme, where the standard rules of radiative transfer begin to warp. The most straightforward explanation invokes the colossal power of magnetism, taken to an almost unimaginable extreme. Near a newborn protostar, magnetic fields can be amplified to staggering intensities, billions of times stronger than Earth's field. In such a ferocious magnetic environment, a quantum effect called the Zeeman effect comes into play. It causes the emission lines of molecules like water or methanol to split into multiple, closely spaced frequencies, each with a distinct polarization. Under normal cloud conditions, this splitting is tiny and hard to measure. But in the maelstrom around a massive protostar, the splitting could be so severe that it effectively isolates one circularly polarized component of the master emission. The cloud's magnetic vice is so powerful, it literally twists the light as it is born, imprinting its ferocious strength onto every photon. However, some observations suggest the magnetism alone might not be enough. The circular polarization can be too strong, too pure, for even an extreme Zeeman effect to explain. This points to a more complex and poorly understood dance within the maser medium itself. The process of stimulated emission, which gives masers their coherent power, might be interacting with the cloud's turbulent motions and magnetic fields in a way that amplifies circular polarization selectively. Think of it like a feedback loop in a cosmic amplifier. Certain spiral motions of the gas or specific alignments of molecules within the magnetic field could favor the amplification of one-handedness of light over the other, creating a runaway effect that results in the intense signal we detect. Our current models of radiative transfer, how light moves and interacts with matter in these dense magnetized plasmas, are simply not sophisticated enough to fully replicate what we are seeing. The circularly polarized maser is therefore a laboratory for physics we cannot recreate on Earth. It hints at a regime where coherence, magnetism, and hydrodynamic turbulence meet, generating an optical phenomenon of startling purity. Each detection is a direct probe into the most ordered, most violent magnetic heart of a stellar nursery, a place where the forces that shape stars also twist the very fabric of the light they emit. The spiral dance of circularly polarized light reveals a hidden order, but within the same nurseries, another rhythm pulses with the slow, steady patience of a living heart. Deep inside the dense cores where protostars are taking shape, telescopes have begun to detect a subtle, repeating pulse. These are not the random flickers of variable brightness, but quasi-periodic pulsations, regular beats of light and energy that repeat over days, weeks, or months. They appear across the spectrum, from the radio whisper of excited molecules to the infrared warmth of heated dust, and even in the X-ray flash of superheated gas. It is as if the entire cradle of a newborn star is gently throbbing in time with a secret, internal clock. This cosmic heartbeat is one of the most captivating final mysteries, for it suggests that even in the apparent chaos of creation, a profound regularity can emerge. The leading explanation for this rhythm is a story of feast and famine on a stellar scale. A young protostar does not pull gas from its surrounding disk in a smooth, steady flow. Instead, material builds up at the disk's inner edge like water behind a dam. When the pressure becomes too great, the magnetic barrier holding it back suddenly breaks, and a colossal flood of matter cascades onto the star's surface. This violent accretion burst releases a tremendous surge of energy, lighting up the entire system. Then, the dam reforms, and the cycle begins again. The observed pulsation could be the flash of that periodic feast, the heartbeat of the star's growth, pounding out the rhythm of its episodic nourishment from the surrounding cloud. But there is another compelling possibility, one of celestial choreography in the deepest dark. Perhaps the heartbeat is not from a single star, but from a pair locked in a tight, dusty embrace. Imagine a binary star system forming so close together that they share a common envelope of gas, still deeply embedded within the molecular core. As these two infant suns orbit each other, their gravitational dance would periodically disturb the inner edge of their shared disk, triggering bursts of accretion onto one or both stars at the same point in every orbit. The heartbeat, in this case, would be a direct timer, its period matching the orbital period of this hidden, embryonic duo. We would not see the stars, but we would hear the clockwork rhythm of their gravitational waltz. A third, more holistic idea suggests the pulse is not from an event, but from a structure breathing. The entire protostellar envelope, the vast shroud of gas and dust collapsing to form the star, could be oscillating as a whole. Like a giant bell ringing after being struck, or a water droplet vibrating after a splash, this immense cloud of material could have natural resonant frequencies. Turbulence or a minor instability could set it ringing, causing its density and temperature to pulse in a slow, regular wave. The observed heartbeat would then be the entire stellar womb resonating, a global sigh from the cloud itself as it concentrates its mass into a new sun. These quasi-periodic pulsations are a fitting final signal because they synthesize so many of the mysteries that came before. They speak of hidden dynamics, like the orbital clocks of distant fast radio bursts. They hint at violent magnetic processes, like those in circularly polarized mesas. And they reveal the intricate, layered structure within what we once saw as simple blobs of gas. Each steady beat is a reassurance and a challenge. It tells us that within the furious, chaotic storm of a star's birth, there is a pulse, a rhythm, a signature of underlying physics we are just beginning to hear. The clouds do not just randomly collapse, they resonate. They do not just chaotically feed, they measure out their material in great rhythmic gulps. In the end, the heartbeat is a promise of order in the chaos, a final whisper that even in the darkest, most turbulent nurseries of the cosmos, the universe is keeping time. These 25 signals, from the mighty gunshots of fast radio bursts to the subtle chemical quirks of deuterium fractionation, paint a portrait of a cosmos far more complex and communicative than we ever imagined. They all share a single, profound origin, the dark, cold, interstellar molecular clouds we once thought of as simple, silent nurseries. Instead, these clouds are cosmic symphonies, broadcasting in every wavelength, from the faintest radio whisper to the most violent gamma-ray shout. They are not voids, but vibrant frontiers, each unexplained signal a locked door to a new room in the mansion of physical reality. What these collective mysteries teach us is humbling. Our current astrophysical models, while powerful, are still sketches. They can describe the calm, but they struggle with the storm. They can map the gas, but they cannot yet fully explain the ghostly halos, the deceptive mimics, or the perfect rhythms that emerge from the chaos. Every anomaly is a gift, a signpost pointing exactly where our understanding ends and true discovery begins. So the next time you look up at a dark patch in the Milky Way, like the coal sack or the Great Rift, do not see an emptiness. See a canvas. On it, the universe is writing in a language of light we are only beginning to learn, with words made of antimatter annihilations, molecular handedness, and magnetic spirals. The greatest chapters of this story are not yet written. They wait for the next generation of telescopes to listen more deeply, for the next curious mind to ask a new question, and for all of us to remember that the darkest places in the sky hold the brightest secrets, whispering to those willing to hear the universe think out loud.